Welcome, everyone. My name is George Noah. I'm CTO of Hyperstratus. Hyperstratus is a Silicon Valley-based cloud computing consultancy. We were founded by executives that have very deep experience in corporate IT and enterprise software and global consultancy. And our primary service we provide to our customers is providing cloud computing strategies and assisting them in evaluating various cloud computing architectures that would be specific to their applications. Typical of our customers is that they already have traditional applications and they're trying to explore the issues and methods for best porting them out to the cloud. We also provide cloud computing training and workshops. I'm going to begin this. This particular webcast is broken into three sections. The first section is Introduction to Cloud Architecture. The second section is a review of the Amazon Web Services cloud platform. And then the third is a review of application architectures and best practices specific to the Amazon cloud. So let's start off with what is the cloud and their various possible definitions. And the definition that Hyperstratus likes is the UC Berkeley RadLab definition. In effect, it starts with the premise that a cloud provides the illusion of infinite computing resources available on demand, and the consequence of this, it eliminates the need for typical upfront planning and provisioning of cloud resources. It also means there's typically no commitment. There is no upfront commitment to use any cloud resources. In effect, you pay by the drink. You pay as you go. This has consequences is that, in fact, then you have, in fact, because you have the illusion of unlimited resources, you can utilize components on an on-demand basis. You could dynamically scale to meet load. You also, though, have the option of not having to deal with issues associated with over-provisioning, which is in effect a waste of capital, or under-provisioning, where you decided not to upfront allocate resources simply because it would be too expensive in a more traditional IT data center. Usually CFOs like cloud computing because it's an interesting transition from capital expenditures to operational expenditures. It's usually better for the bottom line. Cloud services generally fall into three generalized categories. At the lowest level, primary level, is infrastructure as a service. This would be core basic computing capacity and space and networking access. On top of the infrastructure as a service is platform as a service. Examples of this would be the Google App Engine for Python and Java, or Windows Azure for .NET. These would be cloud platforms that are used to run that function as application servers. And at the top of the cloud computing stack is software as a service. And examples of this would be the Google Gmail or Salesforce.com. In general, the overall distribution, commercial distribution of these various cloud offerings can fall into a broad spectrum. But we see that usually at the bottom is the cloud computing as an infrastructure as a service, which would be Amazon and Rackspace and GoGrid. Some companies such as IBM and Terramark provide private cloud infrastructure as a service. For a public cloud platform as a service, you would have Google Apps and Microsoft Azure. And then at the very top for software as a service is typical Salesforce and Gmail. Another way of visualizing the market space here of cloud offerings is to distinguish between isolated cloud services that would be running in your own resources or data center, or shared resources that would be multi-tenant and would be shared by a large set of users. And then also the issues to whether it's public or private. A private cloud is in fact a cloud that's only which you control and access to your resources, and you're the only customer of your resources, versus a more public cloud where you're out there in the multi-tenant environment. So typically we'll see that Amazon Web Services fits in the upper right-hand quadrant. It's a public shared cloud. On the lower left-hand side, we'll have cloud offerings that are run locally in your data center. A classic example is Eucalyptus, which is a an open source cloud offering that you would run in your own data center if you had your own server farm. A good example of a successful cloud application that was well ported to Amazon was TC3. TC3 is a medical claims, insurance claims processing a company. They were typically they provide services that process medical claim forms, and they had been providing a service that only processed current medical claims. And then someone said it'd be a great idea to actually process old historical claims. What happened as a consequence of that is that their growth shot up from 1 million insurance claims per day to a little over 100 million insurance claims per day, and this growth occurred within 1 week. And as to be expected, after a couple of months, the overall load on their system started to drop down significantly as people caught up with their backdated insurance claims. In a traditional data center solution, this would have cost them approximately $750,000 just for new hardware, and about $30,000 a month just to do maintenance and hosting. Using Amazon Web Services, their total cost came out to $600 a month. You can see it's quite a substantial savings. Now, on the topic of clouds, it's also important to understand a little bit about the core infrastructure of their architecture. So typically, a common accepted perspective now on cloud architecture is a cloud taxonomy that was introduced by Christopher Hoff. It was specifically referenced in the Cloud Security Alliance document. It just shows that, in fact, the three structures are infrastructure, the three basic components of the cloud for infrastructure as a service and for platform as a service and software as a service are actually layered on top of each other. In fact, then having a good, well-deployed infrastructure as a service component, you can then provide on top of that a platform as a service offering, and then even on top of that, you can leverage the platform as a service to provide software as a service. A more detailed view of the components of infrastructure as a service and platform as a service is highlighted by this diagram, also originally extracted, as I said earlier, from Christopher Hoff. As you can see here, the basic components of infrastructure as a service fall down into, as one would have expected with any data center, power, air conditioning, heating, floor space, raw computing capacity, meaning core machine, physical machines and CPU capacity, raw networking support, SAN-based or other disk storage services, virtual machine management services, grid and clustering, the ability to manage your images, the actual images of the virtual machines that are running in the cloud. That in itself is an entire technology that needs to be understood. IP address management and assignment and DNS services are also a significant component of infrastructure as a service. Also load balancing and transport services, how to distribute load requests for either web services, incoming HTTP requests, and so how they get distributed out across multiple Apache web servers. Security services, also very significant. We need to make sure that each account, or in other words, each customer of a cloud only has access to their resources and therefore can identify themselves accordingly. Also, identity management. Core components of cloud computing is how can they ensure that only your specific machine images are the ones that can be launched and executed by yourself or designated partners. Most of the infrastructure as a service, cloud providers also provide some form of an API. In the case of Amazon in particular, it's a web services-oriented API. Usually on top of infrastructure as a service is where platform as a service is provided. Typical components there would be database services, meaning usually simple database services, but in certain scenarios might actually rather full query-capable, SQL-capable databases. Generally, it also includes messaging and message queuing. Of course, as I mentioned earlier, application servers, meaning like as in the case of Google App Engine or the Azure.NET engine. Typically, also, platform as a service has its own identity management and authentication infrastructure. And I highlighted here just so that it can be the same as, but need not be the same as, the infrastructure as a service, identity management infrastructure. I wanted to then bring up the point that, here, that Amazon Web Services is an EC2 infrastructure as a service environment. It has a RESTful Web Services API. But Amazon Web Services also has other components, and sometimes people have a tendency to think of these components also as infrastructure as a service, but they really are not. They are platform as a service. These include the Amazon Simple Queue service, their Simple Database service, and their CloudFront service, which is actually a content management service. Google App Engine, as I mentioned earlier, is a more traditionally accepted and understood to be component of platform as a service. I'd like to go into now just a quick and rapid overview of Amazon concepts and considerations. I have quite a few slides on the subject, so I may actually skip some of them to make sure that we stay within our allotted time limit. All right. Amazon Web Services, as I said, consists of both infrastructure as a service components and platform as a service components. So the core Amazon Elastic Compute Cloud, or EC2, that's a classic infrastructure as a service component. Common used component of Amazon called Simple Storage Service, which allows you to store files or large data sets out on web accessible, through web accessible URLs. Well, that's actually again, infrastructure as a service. Elastic Block Storage is, of course, infrastructure as a service component that allows you to allocate volumes, physical disk volumes, similar to server area network storage volumes that you can then format and attach onto your virtual machines. SimpleDB is an Amazon Web Service. This is a very simple database. Simple Queuing Service is a simple message queuing service provided by Amazon. CloudFront is really more of a content delivery network, which allows you to stage web content from S3 and have it staged out on the edge of the internet. And all of these services, in the case of Amazon, whether it be infrastructure as a service or platform as a service, they're all managed by a consistent AWS Web Services API. A little bit of overview now on some of the components of Amazon taxonomy. We see that, as we pointed out earlier, when one has virtual machines, one has to have a way to store the images, the actual virtual machine images that would get booted up and launched in these virtual machines. And so the way Amazon does that is by storing them under S3. Typically, then one can consider these S3 images to be the equivalent of gold master virtual machine images, meaning they're not intended to be modified. Once burned and mastered or bundled, as their terminology, to use their terminology, the S3 image can then be reused time and time again in as many virtual machine instances as you want to start up. The basic raw compute component of infrastructure as a service is Amazon EC2, typically referred to as Amazon EC2 instance types. The various types of compute services usually refer to the amount of CPU capacity that the virtual machine has. Amazon has their an internal networking structure established for their entire web services. It's broken into regions, availability zones. IP address management is a specific component of Amazon Web Services, and I have slides that will go into that in further detail. And there's a security component to Amazon, which usually involves network firewalls and then access control lists that define who can access the individual S3 files. Components that are part of the Amazon AWS offering, but actually fall into platform as a service, as I said earlier, and just repeating to make sure we understand this, is that message queuing and database, SimpleDB, fall under the category of platform as a service. I think it's important for us to understand a little bit about Amazon networking and how Amazon has laid out its overall computing resources. So Amazon EC2 locations are composed of regions and which contain availability zones. A region is a set of one or more availability zones that are geographically dispersed in separate geographic areas or countries. An example is U.S. East Coast versus EU West, meaning Western Europe. Availability zones can be thought of as distinct data center locations that are engineered to be insulated from failure from other zones in the same region. Since they're located in zones that are located in the same region, provide inexpensive, low latency network communication between the zones. An example would be U.S. East A1 and U.S. East 1B. These are the actual Amazon names for these zones. This gives a better, quick review of the general relationship here. As you can see, U.S. region and the EU region are interconnected through the core internet backbone. But within the region, the various Amazon availability zones are interconnected using their own private, redundant AWS-controlled network, which means, in effect, then, that communications costs are much lower when communicating between virtual machines that are within the same U.S. region. If you needed to communicate, let's say, from U.S. region Zone A1 to EU region availability Zone A, you'd end up having to go over the internet backbone. And, of course, that would lead to extra costs, extra communication costs that Amazon will bill you with at the end of the month. EC2 and AMIs is an important concept to understand. Since EC2 just provides raw compute capacity, in other words, you just agree to purchase on an hourly basis a specific EC2 virtual machine instance that has a certain CPU capacity and a certain amount of virtual memory. But you still have to define what is the image, the virtual machine image that you want to start up and boot within that instance. These are referred to as Amazon machine images. The Amazon machine images themselves are signed and encrypted. If you build your own Amazon machine images, they're signed and encrypted by using your own user-specific X509 keys. So, in fact, really, the only entity that could access and boot up your Amazon machine image would be Amazon itself or yourself as a user. No other user would be able to boot up the Amazon machine image unless you had granted them access. And I just want to emphasize then that the Amazon machine image is best understood as the gold master image of a fully configured virtual machine. Once you have an Amazon machine image, you can launch or boot up as many EC2 virtual machine instances as you wish. S3 is where these AMIs are stored. They're stored as a bundle of small segmented 10 megabyte files. All together, they make up the entire virtual machine image. Users can create AMIs from scratch, meaning they do a physical to virtual transformation. If you already have a physical, let's say you already have a physical Linux box, you can go through a P to V transformation and bundle an AMI image for yourself directly based off of your physical machine, or you can use pre-built public AMIs and just run them as is, or you can use a public AMI and then make modifications to them and then store them as a new AMI. When you do create a new AMI, you can't write over the existing one. You actually create a new additional AMI. It's different than the original one. EC2 itself as a computing service is based on Xen hypervisor. So with very significant constraints, if you're already familiar with Xen, then you shouldn't have any problems understanding the basic issues associated with an Amazon EC2 instance. In general, then, when you allocate or you agree to purchase use of an Amazon EC2 instance, Amazon will charge you based on the EC2 compute unit. The EC2 compute unit is, they define it as the equivalent of a 1.2 gigahertz Opteron or Xeon. Compute capacity is in granular levels, so you can get it from either a one-core VM instance at one compute unit, and you can get it up to an 8-core VM instance at 2.5 compute units, meaning at 2.5 times the capacity performance throughput of a 1.2 gigahertz Opteron. Virtual memory also ranges based on the EC2 type. You can get as little as 1.7 gig. I mean, basic three ranges, 1.7 gigabytes and 7.5 gigabytes and 15 gigabytes. Now, by default, when you set up an account, you're really only allowed 20 VM instances, but one can contact Amazon rather easily and ask to have your quotas increased. But by default, any user that just sets up an Amazon account can only start up 20 instances. I wanted to emphasize that the EC2 compute unit is not guaranteed to be an Opteron or anything, but in fact, Amazon will always has the right to swap out the underlying commodity hardware, but they do periodically run benchmarks to ensure that you are getting what you're paying for. Wanted to emphasize now a little bit on local storage. The EC2 instance itself has a default local storage, as I point out here, ranging from 170 gigabytes to 1.8 terabytes, depending on which type of an instance you're running. But the point is that it's ephemeral, meaning that once you shut down that instance, all that evaporates. And we'll go into that in more detail. It's a very significant issue to bear in mind. The other type of storage is the elastic block storage. This can be thought of as an actual disk volume, similar to a SAN disk. The maximum size that Amazon currently supports is 1 terabyte, and currently you're allotted maximum quota of 20 of these EBS volumes. But again, you can contact Amazon; they can make arrangements for you to get additional ones. EBS volumes appear to your EC2 instance as if they're mounted file systems. You have to format them, and you have to actually mount them. They give you higher reliability and lower latency than if you were using the internal default storage. Key point about EBS is you can also do live snapshots to S3. So you can take incremental snapshots and develop a backup strategy based on these. Just a quick mention here about S3. You may not be aware, but many of the websites you go to today, if you look at the URL for various GIF files or images, you may see that it contains s3.amazonaws.com. That means that image or that streaming media file, whatever it is actually being stored under Amazon S3. The key point to remember is that S3 areas is located specifically to a region, and one of the things that is nice about S3 data storage is it's automatically replicated within the region to multiple zones. The real issue here with the ephemeral storage that's in the default EC2 instance, all data is lost when you terminate that instance if it's ephemeral storage. It's analogous to having a Linux live CD that you can boot up. It's a live CD, you can boot it up, you can create files on it, but once you shut down that Linux live CD, you've lost any data that you might have had stored on your RAM drives. This is a major constraint. So the way most people work around this is that they'll actually launch their AMI image from S3, and then after the image is up and running, they'll then extract whatever dynamic data they need from S3, and then before they terminate their running Amazon virtual machine, they'll save the data back into S3 so that later on a reboot they can get it back. Alternatively, typical dynamic data usage pattern is that they'll launch from S3, your AMI image, remember, is stored under S3, but they'll use elastic block storage as a persistent volume. They'll attach the storage that would have been previously formatted, so they'll just mount it. They can then just store data, read and write to it as needed. If the machine is shut down, all data still persists within the elastic block storage. Another thing to bear in mind about Amazon is the issues associated with virtual store, with the assigned IP addresses and DNS names. These are dynamically assigned. So for any given instance, virtual machine instance, you have a dynamically assigned IP address, and if you really wanted to communicate internally within the Amazon AWS cloud, you're in general going to end up using dynamic DNS registration services just so that your Amazon instances can publish what their dynamic IP addresses are to each other. I think the key point to emphasize then is that there really is no control of the IP addresses or DNS names that are assigned to your initial instance. There is the ability, however, to have an allocated elastic IP address. These are persistent IP addresses and DNS names. They're a limited resource, so Amazon really doesn't give you very many of them. But these are traditionally used only for web-facing applications. So if you bring up a VM that has an Apache web server, you can then, typically after the web server starts up, you then assign an elastic IP address to that web server. At that point, now that web server is accessible through the persistent elastic IP address or DNS name. Wanted to emphasize then that you would not use elastic IP addresses for internal servers such as Tomcat servers or other internal components you might have in a multi-tier web application. The security for the security mechanisms that Amazon provides are network security groups, which are basically a collection of network traffic rules for incoming connections, and access control lists, which are used to restrict who can get access to the S3 files. Obviously, if you were at a website that has a streaming media that is being stored on S3, then it's obviously for everyone. Right? Everyone has been granted access under S3, or else it wouldn't be public. Another component of AWS is the simple queuing service. It's a very simple, reliable message queue service. And generally, you really can't have very large messages, but you can put in 8 kilobytes of data per message. It's interesting that they don't guarantee it to be a FIFO, first in, first out message queue, so you have to code accordingly to address that. SimpleDB is again another Amazon service. Provides a simple ISAM-like MyISAM database service. It's typically used to store typical configurational information associated with the virtual machines. Sometimes you might use it as an alternative to dynamic DNS. You could, for example, just store individual records for each of the VM instances that have been launched, store their configuration information in them. It's very similar to MyISAM. It's very limited, though. It is very simple where search criteria, no capability to do table joins or anything like that. Definitely no support of full SQL grammar. The slide here identifies some of the details of the constraints for SimpleDB. Well, having quickly run over these basic components then of Amazon EC2 instances, S3, EBS, Amazon Simple Queuing Services, and Amazon SimpleDB, and emphasizing that, in fact, there is a constraint on the ephemeral storage of the EC2 instance and that the IP addresses are dynamically assigned. We should now try to discuss, well, how do you design an app, a cloud application architecture that would be appropriate to run in this Amazon environment? Well, we should start off with some basic design attributes that always bear in mind. One is that they should focus on what your needs are, not on the hardware specs. But bear in mind, this is a cloud environment. It's an on-demand environment. You pay as you go. So you do, in effect, you try to search for on-demand provisioning. You really only should try to structure it so that you allocate resources as you need them and only the amount that you need. You should also structure it so you can dynamically allocate resources as or down, and dynamically scale down resources depending on real-time load. Bear in mind that you always bear in mind that you don't have any upfront costs. Optimism is an important thing to keep in mind here. Is that because the machine instances are starting up, preferably if you structure it appropriately in an on-demand configuration, then each instance has to be able to dynamically identify itself and publish what its configuration is, and also figure out what its relationship is to the other virtual machines that might be existing in a multi-tier cluster. So in general, there are 10 best practices that one should try to adhere to. I think the first one is really more of a buzzword perspective. You should do cloud apps, not just apps in the cloud. Make an effort at identifying a structure for your application that is appropriate to the cloud, not just a simple straight port. You should try to virtualize the application stack that makes up your cloud application. Very important that you design for failure, because if you design for failure, you've done it well, but in effect nothing actually can fail. should design for scalability. Make sure that you can leverage loose coupling so that you can maximize plug and play and really take advantage of scalability. They cannot emphasize it enough. You have to design for dynamism. You need to build security into every component. And in fact, what the cloud is really suggesting is that you should have a deep perimeterized security model. Every component, every virtual machine should be should have self-contained security infrastructure, and really she can't even make any assumptions that you're, at least if you're in a public multi-tenant cloud, you really shouldn't be making any assumptions as to what other virtual machines might be running on the same base platform. Leverage native cloud options as best you can, because they're generally going to give you the best performance and usually give you a better dollar value. And leverage, you will see we'll need to really leverage cloud management tools. And the last thing is, don't fear these cloud constraints. They may be rather daunting at first, but keep an open mind, and you'll find that you'll be able to be very successful in your projects. Here's an example of a traditional cloud application as we might see it in a data center. There's a load balancer, web tier, a business tier. Typically what happens is that then you have a separate set of database servers that are being used for backup, and messaging and so forth is usually managed by another subsystem. So this might be, for example, IBM MQ for messaging. Business tier might be application servers, Tomcat or WebSphere. By WebSphere, of course, is just typical Apache. Well, if you consider ways to structure this so that we end up with a more virtualized application stack, and I can see that something didn't quite work right with this slide. We're missing a few here, but a few components here. But basically, you need to understand that you have a load balancer that goes out to web processing units, which then goes to the business processing units. And notice the key distinction is that in this environment, we had separate machines, physical machines located in a typical environment of verify, control, and execution. We try to establish that when you launch a virtual machine, you'd already had one instance of a virtual machine might be able to utilize those all three components itself. You need to really be careful then of the ephemeral storage. I know I've emphasized it a few times, but it is important to bear it in mind. It is an issue that really cannot be understated. In effect, if you're going to use, the main point to realize is that if you're going to use a database, you should always be using EBS volumes. One point to bear in mind on ephemeral storage is that if you are using EBS volumes, rather than having a large number of small little EBS volumes, you might even want to consider some tricks, such as having one large NFS server that has a large EBS volume, and the NFS server then is providing access to your smaller EBS directories or folders within that EBS volume. If you're going to then also have to compensate for the dynamic IP addressing. Particular situation that you have to be aware of is the load. If you're going to run load balancers such as a high availability proxy, HA proxy load balancer, it needs to understand what are the IP addresses of these dynamically started up EC2 instances. Common thing to do is to use DNS, CNAME registration, or alternatively, you can use entries in SimpleDB. Another point to emphasize is that if you are going to do multi-tier architecture, you should really leverage EC2 instance communication that is internal to the zone or the availability or the region. In other words, avoid going across the public internet backbone. A design for failure. It's an interesting quote here from Werner Vogel. Everything fails all the time, so it's a clear statement from Amazon. Bear in mind that Amazon as an infrastructure as a service provider does not guarantee that their services are running 7/24. They have limited SLAs. But they do provide you the illusion of infinite resources, so you then can leverage that and avoid single points of failure. If you assume that everything fails and design backwards, then in effect your application won't fail at all. Kind of things that can fail under EC2, well, your EC2 instance, meaning your virtual machine might crash, and your multi-tenant and multiple virtual machines running on that box. Portions of the zone might not be accessible. These are usually your cases when there's some type of an internal networking problem to Amazon. They have happened in the past. You need to address them. If your zone is not accessible, then you may not be able to launch your EC2 instance, or you may not be able to mount your EBS volume. These are things that can actually happen. Much less frequently is, in fact, I don't recall within my conscious memory of region-wide failures. If a region were to go down, then your entire S3 bucket or your entire simple DB database would disappear, or your simple queuing service queues would just disappear. So therefore, you really need to use fault-tolerant features. In particular, then, if you have an Apache web server, use elastic IP addresses. These are these fixed, constant external IP addresses. Why? Because they're fixed address. If a Apache web server were to go down in one particular zone, or you're having a problem with the zone, you can bring it up in another zone and then just assign that external elastic IP address. Use multiple zones. Use EBS or persistent file systems and leverage the use of snapshots for backups. You may want to then have replicated EBS volumes using, for example, rsync as a way to do real-time synchronization of EBS volumes across availability zones. You also may want to create multiple DBMS flows if you're running MySQL, for example, as part of your application. Create MySQL slaves in different availability zones. And leverage real-time monitoring services, either from Amazon itself or CloudWatch service, or services provided by RightScale, which I'll mention later, is a cloud management service. Design for scalability. Really need to take advantage of characteristics of a scalable architecture. A scalable service will always prove to be resilient to single-point failures. In general, we'll do more discussions here, but in general, you want to take advantage of loose coupling of processors and requesters. Take advantage of load balancing. And here I think I'll have, on the topic of loosely coupled systems, you want to take advantage of independent components, and where possible, take advantage of message queuing service. Here's an example of a tightly coupled system where some processing came in and was done in case of a tightly coupled environment. Was done with controller A, then it passed to controller B, then to C. On the other hand, if you use message queuing, the request would go into the queue. You would have a cluster of EC2 instances that would then be able to pick up requests from the queue and pass them on down to the next cluster of resources, and so forth. So this is an example of something that would use SQS or Unit to pass along requests. Design for dynamism, meaning you can't assume the health of any fixed location or component. Your instances, when they start up, have to be able to perform self-discovery. Through the use of something referred to as EC2 metadata API, they can find out who they are, what their configuration parameters might be. If not, if it's very complicated, alternatively store their configuration data in SimpleDB. Security, well, as I mentioned earlier, you should really utilize a deperimeterized security model. If you take advantage of the existing EC2 security groups, they allow you a fairly reasonable degree of inbound rules, at least restricting what external IP addresses are able to connect into various ports on your EC2 instances. If you are going to store data under S3 or even under DBS, you really should consider encrypting the data. I cannot emphasize that enough. And of course, if you're going to be communicating, you really should, meaning if you're going to communicate sensitive data, then you really should be using SSL as a core TCP/IP data encryption mechanism. Leverage various storage solutions. I think I've gone through that quite significantly. And leverage management tools. Now, the two basic tools I'd like to introduce very quickly is RightScale and Kievo. The management tools that are provided by Amazon are very, very simple. So there, in fact, is a little aftermarket ecosystem that's specific to Amazon, specific to the Amazon API. In particular, then RightScale is a company that provides very reasonable and robust and very rich provisioning and monitoring of your Amazon environment. And Kievo is another alternative mechanism, but the dominant player now in the marketplace is RightScale. Some of the typical elementary tools that are provided is the Firefox plugin called ElasticFox, or a S3 browser called S3 Organizer. These are very elementary. You really do want an advanced tool that allows you to manage the attaching of EBS volumes and the assignment of the static EIP addresses. I refer to this as the Cloud Deployment Management System. It really should allow you to have a standards-based event notification service so you can tell when your utilization of a given EC2 instance is maxing out and you need to provision additional ones. The RightScale management tool environment is a script-based environment. It's very, very common sense if one is for example, a Linux admin user. It's quite logical. It even has its own internal version control system internally, so you can keep different versions of these scripts as they evolve over time. It has incorporated within it is full automated auto-scaling and remediation and notification and alert system. And it allows you to collaborate within the system between application developer and network administrator and so forth. Typically, the RightScale environment really is structured as an intermediate proxy. So you yourself, as a user, would interface with RightScale by going to their Ajax Web 2.0 application site. RightScale then will communicate with the Amazon Cloud using the Amazon API, and then the Amazon Cloud is then going to launch your instances, your individual VM instances. The particular thing about systems such as RightScale is, in this example to highlight here, is that when your virtual machine instance actually is finished booting, it notifies RightScale that it has finished booting. Then RightScale can inject additional management scripts and provisioning scripts into your instance. For example, you may want to install. In certain cases, for example, the virtual machine might not even have Apache installed, but the RightScale provisioning scripts would install Apache and dynamically install Perl and a complete LAMP stack. And in general, that might add another 5 or 8 minutes to the machine boot, but if you think about it a minute, you can now have one very simple, clean AMI image, and the customization of the AMI is something that can now be done right at boot time. Of course, there's a downside that you do need to spend an extra 5 or 8 minutes just to do the provisioning. Likewise, when you want to shut down your virtual machine, the RightScale environment allows it to send specific scripts that would basically shut down your application. Aspect of how RightScale performs its management is that RightScale is able to maintain through the use of CollectD, which is a popular Linux framework to acquire statistics metrics on machines. So RightScale provides its own CollectD server and really integrates it all into their framework. So in a very standardized way, if you're a Linux user, for example, this would make perfect sense to you. By contrast, Amazon itself has its own service called CloudWatch. It's still an evolving service. There is an API for it, but not many of the management systems have actually fully gotten on board with CloudWatch. If you contrast this with Kievo, Kievo is similar to RightScale in the sense that it is an intermediate proxy, but Kievo has a complete integrated workflow management system integrated within it. So Kievo can do quite extensive processing of events and it can respond to events by very elaborate workflows, not just simple simplified sequence of scripts, but can actually evaluate conditions, make decisions, conditional and execution of various adjustment actions. I know I've gone rather quickly here, but the main point to emphasize then is that if one is going to be using Amazon Web Services, one needs to bear in mind the consequences of the ephemeral storage issues and the dynamic IP issues, and one should assume then that one should be structuring the application to leverage a very dynamic environment. It should be dynamically scalable and have no single point of failure. If you'd like additional information, you can always go to our website, hyperstratus.com. Right on the home page, at the bottom of the home page, there's a reference to a white paper that we provided doing analysis of a port of a lamp, typical lamp application for a customer of interest, that it has a total cost of ownership analysis, a TCO analysis. Could be very interesting for people to explore the financial benefits of doing a cloud port. And it also goes into a rehash of some same things I did here regarding ephemeral storage and dynamic IP address. We also provide cloud computing workshops via Unitech. If you go to our website and click on our training tab, you'll see links there for our various workshops. And of course, you can always send me email at george.noah@hyperstratus.com. Catherine, I return it back to you now.
Okay, thanks, George. I hope everyone can hear me. I'm in San Francisco. We're actually having a big storm, and I'm on a landline that I don't usually use in case the power goes out. So bear with me. I understand I'm quiet. So, George, you actually covered a huge amount of material, and I know you told me you would, but it was amazing. A couple people have asked if you're going to share your slides afterwards, and I know you talked about that.
Catherine, I'd like to make them available to you as a PDF file for you to then distribute them according to O'Reilly policy.
Okay, I think I'll put them on our SlideShare site, and I'll send everyone a link to let them know where they can find it. Or if you just want to go to SlideShare, it's slideshare.com/O'Reilly Media, and they'll be posted there shortly after this presentation. So Tom is asking, are there any case studies on utilizing SQL replication or Windows case studies that you can refer them to?
The question was specific to SQL databases. Maybe I misunderstood the question, but was it specific to replicating SQL databases?
I believe so.
Yeah. In our case, our white paper, the particular, this was based on MySQL, and we do give a brief discussion of the configuration that would have a replicated MySQL server in the white paper. But offhand, I just can't really come up with a reference. I'd have to go do some Google searches specific to that.
Okay, fair enough. And I want to encourage people, if you have any questions, please type them into the chat room now, because I know that George talked quickly and covered a lot of ground. So if you want a clarification on anything, now's your chance. So, George, there was a question earlier, and you may have covered it. Someone was asking you if you would please talk about the Amazon Virtual Private Cloud.
Yes, I didn't mention that in this presentation specifically. Amazon just recently announced a feature which they refer to as Virtual Private Cloud. What it really is an IPsec virtual private LAN. So what it allows you to do is to define an IPsec VPN, virtual private network, within the cloud, within their cloud, and your EC2 virtual machines would then be started up within your VPN. That means then that however, the IP addresses would still be dynamic, but they would now be assigned from your VPN subnet range rather than the general Amazon IP range. It also means, though, that then all communications between your VM instances running within the VPN would be done under IPsec security. And the other thing to bear in mind is that, at least with the current status of the Amazon Virtual Private Cloud offering, the VMs or EC2 instances running under the VPN cannot directly connect to the external internet. So if they do try to connect to the internet, they would end up getting routed back to your data center and routed through your standard communications gateway or and firewall. So just bear that in mind. So that if you have an application, in effect, then this leads to a configuration where the use of Amazon Virtual Private Cloud is very good if you have back-end processors like Tomcats that do some lengthy computation, or that end up doing some number crunching or do some business intelligence analysis, and don't need to go out to access other external internet sites.
Okay.
I hope that gives a brief answer. I think what I needed was a diagram, but
a diagram I was thinking would be very helpful, but
yeah, but I didn't include it in.
That was a great answer. Well, you can include everything.
Yeah.
So here's I saw this question on Twitter. Someone was wondering how inexpensive it is for developers to play with Amazon's cloud environment. And another person, Shrikant, just asked, is there a mechanism in Amazon cloud environment where we can do prototyping or evaluation of the cloud without having to pay for usage? So how do you...
Right. To set up an Amazon account, that is, all you need is a credit card. As a matter of fact, if you are an Amazon retail customer, you're already set up. You just have to go and sign up for the Amazon web service, and they'll just start billing your regular Amazon credit card account. But you may be interested in knowing that I believe RightScale still gives you a free 10-hour, you get a free 10 hours of Amazon access using RightScale. It's a very nice feature. Their intent is to introduce you to the RightScale system as a management interface to the Amazon cloud. But as a consequence of that, you do get, and they don't charge you for that, but you are then allowed 10 hours of compute time on Amazon itself. So you might want to just sign up for RightScale if you don't want to create your own account and put down your own credit card. The costs are actually fairly inexpensive. If the question was how much does it actually cost, well, a small EC2 instance, this is a single core, single compute unit instance, it's 10 cents an hour, which means that if you actually let it run 7 by 24 for a whole year, you would have paid $876, and that is a bit. But at 10 cents an hour, you just start it up when you want, and you shut it down when you're finished, and start it up the next day.
That's very reasonable. So here's
yeah, and if one is, Amazon also has something they refer to as reserved instances, which means that you're willing to sign up for a higher initial rate or a higher upfront payment, then they end up charging a little less per hour. And so if you did sign up, this is for those people that may want to actually run a web service, run an EC2 instance for an entire year under Amazon. If you do sign up for that, for example, a small instance under a one-year plan would only come up to be $490.30 as opposed to $876. But if you're a developer, I would just go with the pay-as-you-go by the hour. The thing to then bear in mind, though, is that make sure you're using S3 or EBS volumes, because once you shut down your system and you restart it again, anything that is not under S3 or not under an EBS volume will just disappear and get reset on the next reboot or relaunch. Will get reset to the AMI image, the original Gold Master image.
Okay. We have a couple more questions. I know we're getting short on time, but if you are willing, let me ask you quickly. One was, again, about going back to the Amazon Virtual Private Cloud. And he wanted to know, is the IP address still assigned dynamically?
Yes, it is, but it's now within your VPN subnet, but it is still dynamic.
Okay. And then John is asking, have you used any cloud solutions other than Amazon EC2? And if so, can you compare the maturity of the offerings?
Yeah, we've also used Rackspace, and that's the key point is systems such as Rackspace don't have the ephemeral storage problem. Sorry, incorrect to even say the word problem, but artifact. So in terms of, I don't have the pricing information right at my fingertips for Rackspace, but it also is it's a stable, mature service. It, of course, does not have the immense resources of Amazon, but it is a mature product.
Okay, and then here's one last tricky question for you. We have a 3-tier application, web server database. We store the name address of the DB at the server level, server at the web level, layer, not level, at the server layer, server at the web layer. So how do we avoid this if we were to use Amazon Cloud for multi-tier applications? In less than a minute, can you answer that?
If they already have a traditional 3-tier, meaning that there is an Apache server, maybe a Tomcat, or JBoss or something, and then a database server, meaning MySQL or Oracle, they may want to still maintain that same overall 3-tier structure anyway, because it allows them to scale up web application independently of the application server processing. Typically, obviously, you wouldn't be launching multiple Oracle database servers based on load.
Right.
So they may want to actually maintain the same environment. They do need to understand that, and of course, they need a load balancer. They could either use the Amazon dynamic load balance service and pay for that, or they could create a virtual machine just to do the load balancing as the front end to the web. And so all requests go to that load balance instance, and then it then directs traffic to the other Apache instances. But they probably are going to maintain the same structure, at least if I understood the question. I don't think they need to deviate from their core architecture as they currently have it laid out. They just need to bear in mind now that they don't have any fixed IP addresses. And so they need to make sure that they have a way to dynamically register the IP addresses of the various servers that make up the tiers.
Okay. All right. Good answer. Well, I think we're about out of time now, but I want to thank you so much, George, for doing this because we get so much.
Yes, and I thank you for, I realize there was quite a lot of information. I went very quickly, but my intent was that the slides will be helpful once they're online, and they will save the readers or the audience a few hours of flipping through through other material elsewhere.
That's true, and we'll also have a recording of the entire webcast available. So I'll send you Don says it was an excellent presentation. Thanks, Don. Yeah, we get a lot of requests for cloud webcasts, so I really appreciate your doing this, George. And everyone, remember you can visit the HyperStratus site to get a copy of the white paper that George referred you to and more information also. So as I said, we'll have the recording available shortly. It'll probably be a few days, and we'll have the slides on SlideShare probably later today, but I'll send you the link when I send you the link to the recording. But if you want to check SlideShare before then, slideshare.com/O'Reilly Media, and you can get the slides there. Thanks, Marcy. So
within a few minutes, Catherine, I'll send you the slides in PDF format.
And I'll post them right away. So I just want to thank everyone for joining us today, and thank you once again, George. And I
Thank you, guys.
hope you all join us again. I'm closing out the meeting now.
Bye.
Thanks, folks.